epsilon curve, you see we don't get anywhere near the failure loads. In fact, if I put those dashed lines in, remember those were the failure loads for the case without soil is failing at about the same load because the soil doesn't know that it's got any extra strength from mechanical stabilization. It's got the same strength parameters as before. So it actually fails, even though you've got membrane element in there. Then what happens is due to tension being mobilized in the membrane, you get a slow increase in the vertical load. But you're going up to here. If you increase the stiffness very high, you could the line go up like that, like it did load test. But that's not recreating the fundamental mechanics of the problem. So you see the sum of the parts just isn't enough. The true performance of the aggregate with the geogrid is greater than the sum of the parts because the geogrid is actually improving the aggregate, and you need to include that effect in the model. So if we go back to the plate load tests that we saw before, and our friend here was rightly skeptical about doubling the stiffness. If we try the new constitutive model, a TSS model as we call it, tensile stabilized saw model, a much more accurate fit. We're getting more of the curvature that we saw before, more realistically, it's continuing to approach a plateau of eventual failure instead of just rising and rising in the case of a membrane element. So it's an example where we've also got a good match with the data, but I think more faithfully recreated the mechanics of the problem there. Yes. So he's happy with that. So those are the stabilization applications. Let's move over now to reinforced saw walls. I'm sure you're all familiar with those. There are a couple of examples. So these are walls with layer upon layer of geogrid extending back behind the wall, mechanically stabilizing or reinforcing the fill that's added behind. So you can support near vertical such as this. These types of geogrid, reinforcing geogrid. Now, before I go into the mechanical stabilization part, I thought it'd be useful just to give you some of my top tips for modeling reinforced saw walls. If ever you've tried to do this, you may have found it rather difficult. Actually, particularly reinforced slopes. I've sometimes tried to simulate reinforced saw slopes that limit equilibrium methods show are stable, and I can't even get the FEA model to stay up to support the thing. It's quite challenging to model these structures. So here are some just general tips from my own experience of modeling these types of structures before we get into the mechanical stabilization part. The reason I'm recreating a laboratory trial wall, that's why it's got these limited dimensions here. So a backfill model and parameter here. That needs quite an advanced model to get realistic output. If you just use a basic linear elastic, perfectly plastic, more Coulomb model, it's going to be difficult, close to actual results, even more difficult than usual. Because there's a large stress change during construction from placing this layer to then placing all the layers above, you get quite a large stress range here. So it's better to have a model that will have a dependent stiffness to take that into account. You also get a lot of yield. So you need realistic prediction of yield deformations, not just elastic. Because at these low stress levels, you get quite a lot of displacement. You need, of course, frictional strength. So good models to use are hyperbolic models such as Duncan and Chang or the hardening saw model. So they're particularly well suited to these backfill materials. Now, regarding wall elements, you've got a choice of using area or volume elements in 3D or just using line or surface elements. Of course, it's easier to use line or surface, but how accurate is that? Well, generally in soil structure interaction, this is considered more conservative because you're losing the effect of the moment effect of friction on the back. When you've got a thickness here, the soil friction on the back of the helps actually to reduce deflections, but you lose that benefit here. So it would normally be conservative, but you've got the joints in the wall facing, which makes it particularly challenging. So walls are made of panels or blocks, so they're not a continuous structural member. So you could put hinges in here, but then it'll be too conservative if you do that. It's a bit complicated because normally when the wall is sufficiently high, you've got enough down drag and compression in here that this will act like a continuous member because the whole thing is in vertical compression. But that won't necessarily happen early on. I found a good way that's worked sometimes is if you put a hinge just at the base, at the toe of the wall, then that works reasonably well. To be more certain, it's better to use the actual area or volume of the blocks or the panels. It takes longer, of course, but that will be more accurate. Now, interface elements. That's often a tricky one with these walls. Where do we put interface elements? Exaggerated 5 times just to help see what's actually happening. And this is close up from somewhere in here. So we can have a look at what's happening. So I found what you need to do is, yes, you need interface elements on the back of the walls. You can to get a lot of settlement of the back blocks stiffer than the soil. So you see this here in the soil was up here. So you do get quite a lot of movement. So that's probably the most important interface element on the back of the wall. You need them between the blocks as well to model that. As I said before, when the wall gets higher, it's all in compression and it's not so important. But early on, there could be some movement between these blocks when there isn't much self-weight. Be careful connection between the geogrid and the block, because if you're putting interface elements here, if you're not careful, the geogrid won't be connected to the block. So just be careful with that. It's a good idea to extend it along here, just make sure that it is connected. And then where people think about interface elements and want to use them is between the geogrid and the soil. I found that that's serviceable strain. So if you're predicting deformations, probably not necessary. But you've got a block between the aggregate and the geogrid apertures. So there wouldn't be any significant sliding between the aggregate and the geogrid. So actually here, I don't use an interface element at serviceable strain levels. If you wanted to use it for ULS design, for internal strength, then maybe you will, but that's quite a big task. I'd still recommend just using limit equilibrium for ULS